Very good day to all the listeners. I'm Anrich Steyn from GLS Consulting in Stellenbosch. I'm an electrical engineer specializing in the field of power systems, and today I'll be talking about geospatial load modeling using a consumption-driven philosophy. So first of all, just a quick overview of what I'll be talking about. So today I'll show how network planning may be achieved by geospatial consumption tracking and forecasting, followed by network load modeling. And I will demonstrate the principle of this interlinked modeling and forecasting process and how it is facilitated by the use of two in-house developed software packages. So first of all, an introduction to the problem. Over the past few years, electricity consumer behavior has changed due to several factors such as energy efficiency, demand-side management strategies, rising electricity prices, and also the onset of distributed generation. So this necessitates a renewed look at load modeling and forecasting, and in this regard, GLS Consulting is actively researching and developing geospatial load modeling and forecasting techniques. So here at the bottom you see an example of a local municipality in South Africa that just shows a quite steep decline in maximum demand over the past decade, whereas traditionally a load growth would typically be assumed in a forecast process, and this just on some level illustrates what we are talking about when we are saying that there's definitely a change exhibited in load behavior. So the two tools that we are using are in-house developed software packages. The first one is called Swift. It is GIS-based software that performs statistical analysis on utility billing data. And then Edison, which is also GIS-based software, but this one is for integrated and simplified electrical network planning. So the way we do the energy consumption analysis is that in our Swift model, we populate each stand with electricity sales data, which is the energy consumption in kilowatt hours, and also the per stand land use data. Then we take this model in Swift and we use that to populate our Edison electrical network model. So other spin-off functionalities that you gain from this is that you can do loss calculations, where you can take a look at your system input versus consumer usage, revenue enhancement through identifying unmetered stands, and then also tariff analysis and cost of supply studies. So the way we do the geospatial network modeling is after taking the consumption and land use of each stand and importing it into the Edison model via Swift, we spatially tie each stand to its closest supply point, and this supply point depends on what level of modeling the user is doing. So you've got the choice to either map each stand to its closest low voltage kiosk, to its closest mini sub, or to its closest substation. Then you get your per stand consumption and your ADMDs, and you roll them up to your kiosk supply point, then to your transformer zones, then to your distribution zones, and finally to your substation zones. And I will elaborate what I mean by the different zones in the next slide. So this facilitates then a bottom-up approach from stand to substation. Benefits of this is now that you have the land use and consumption on a per stand basis, and this eliminates high-level estimation of load class mix in a load area and subsequently then reduces errors in high-level load class mix estimation. Other spin-off practical functionality is the ability to identify customers affected by outages, and then also the ability to view composite load profiles at different supply points, whether that be at kiosk level, mini sub level, at level of a ring main unit, or switching station or substation. And then the functionality also promotes the ability to do low voltage network modeling. So in terms of the spatial resolution, we distinguish between four different zones: the substation zone, which is the entire supply area of a particular substation; then the distribution zone, which is an MV switching station supply area; then a transformer zone, which is the supply zone of the MV/LV transformers, and that includes mini subs, ground and pole mounted transformers; and then ultimately kiosk zones, which is the supply area of a low voltage kiosk. So this is to show you a global network view of a particular client's network where the stands were cross-referenced to the closest MV/LV transformer or mini sub. And then this is the same network. On the top left, you'll see the conductor network. So these are the overhead lines and the underground cables. They are colored according to the substation zones. So every different color represents the supply area of a different substation. And on the right, you'll see the stands included in the model. And that shows you in differing colors from which particular substations the stands are supplied. This is just to illustrate the visual useful functionality that you gain from the cross-reference feature. This is another example of a different client where we did a pilot study. On the left, the red cables you see is medium voltage conductors. The blue low voltage conductors. So this was an exercise to go all the way up to low voltage level and model the low voltage network for the customer. On the right hand side, the cross-reference feature showed here is the stands mapped to the closest MV-LV transformer or mini sub. On the next slide, you'll see on the left the two different colors represent stands fed by two different substations in that particular area. On the right is the same network, where here every stand now is colored different according to the particular MV-LV transformer or mini sub that they are supplied from. This is just to give you a visual feel for the useful functionality that you can gain from this feature and the visibility that you gain into your network. This is just to show that we can go all the way up to the low voltage network. We can model on a per stand basis, and you can also model distributed generation. If we now take a look at the methodology that we employ. So first step is we populate these stands with data. So the data that we populated with is the consumption values in kilowatt hours, and then also the load classes, which we derive from the land use data that we have for each stand. So we input this into our stands, and we currently get that from our Swift database, which is informed by the utility billing database and the prepaid meters database. So after populating our stands with data, we map our stands to our supply points and model dependent. That could be the closest, as I've mentioned, kiosk or mini sub or substation, whatever the purpose of the modeling. Then we calculate theoretical demands, and in this theoretical calculation, we use load factors and power factors, which we obtain from our Edison load profile database, which is currently informed by the National Standard Load Profile Database, or which is typically known in industry as the Eskom GLF standard. So currently we're using the Eskom GLF standard to populate our Edison load profile database. From that we get load factors and power factors for different load classes, and we use that in calculation of theoretical demands. After doing that, we obtained whatever meter demand data we can from the utility. Typically, the high resolution and the low downstream you have it in your network, the better for calibration purposes. What we do is we compare then the theoretical and metered values, and we go through an extensive calibration process. After calibrating, we extract the meter data and the calibration parameters, and we store them in a database. And then we go through what I like to call a refinement feedback loop, a rinse and repeat type cycle, where as we gain experience and we gain more data and we employ the methodology more and more, we start getting to a point where we can update our Edison load profile internal database with new information that we learn through our experience, and then which could ultimately lead to an update of the Eskom GLF standard. So now the problem statement is that we know what our energy consumption is, and in terms of network design, what we're interested in is MDs and ADMDs. And how do we get from this known metric to an unknown? So in South Africa, we all know about the load data problem. That load data is not readily available downstream of HVMV substations. However, energy consumption data is readily available through our Swift database. Now we want to go through a process whereby we can predict the MDs and ADMDs from energy consumption. So if we take a look at the curve here in the bottom, the area under the curve is kVA hours, and that is equal to kilowatt hours divided by a power factor. So we can use this relationship in a calculation process. So we know the kilowatt hour values, the power factors we can assume from the Eskom GLF standard, and then try and calculate a kVA value. I will elaborate on that as we go along. So research has shown customer consumption to be a useful predictor of load profile models for different customer types. So many years ago, previous research has focused on developing a household consumption model, which was then used to inform an ADMD model. However, what we are doing is not developing the household consumption model because we already know through our database what the household consumption is. And then we can use what we know to derive an ADMD model. So just a quick look at the load profile database internal to Edison. We assign profile types according to the land use data imported from Swift into Edison. But apart from importing your load profile shapes, you can also create them, and they are fully customizable. So this promotes flexibility of the software, and the software can then perform functionality with whatever input it is given. So this then facilitates quick and easy testing and verification of different load models. So at the bottom you'll see a breakdown of the different profiles, their characteristics, and also viewing the shape at the bottom. So we normalize the profiles with a 1 per unit peak value and do not assume absolute kVA value. So that is the fundamental difference between the approach that we at GLS employ as opposed to the Eskom GLF standard. So on first iteration in our process, we assume the same profile shape as the Eskom GLF standard, but not necessarily the same amplitude. Rather, we calculate the peak value in relation to the actual consumption data. And the way we do this is by employing this equation here, where we calculate the theoretical maximum demand for a stand by taking the consumption of the stand, dividing it by the load factor times the power factor times the 24 hours in a day. So the load factor aims to provide compensation for using averaged as opposed to peak consumption. And then, as I've mentioned, the load factors and power factor values are theoretical values then assumed from the Eskom GLF standard. So the consumption input can vary. You can use your annual average daily consumption, which is the initial method that we tested. You can use your per month average daily consumption. Then you can use the average daily consumption of your peak month. Or most useful one is that you can use a statistical distribution of your daily consumptions, so that you can reflect some input variability in your demand calculation output. Or then you can also consider your consumption on a monthly basis with no averaging. So this is just to show that the substation, the distribution, transformer, kiosk zone profile is a summation of all profiles within your zones. So at different supply points, you can view composite load profiles and see how its downstream loads summate to form its composite load. So you can view the consumption, the maximum demand, and the ADMD's breakdowns per load class. Then at the bottom, you can see the combined and the per class load profiles. And on the right hand side, you can see the combined consumption and your maximum demand hourly breakdowns. So the ADMD is not really a useful metric when we're looking at the behavior of non-domestic customers, and yeah, particularly referred to commercial and industrial. So there, something that is much more useful is consumption density, kVA per hectare value. So we also import if available, the non-domestic kVA metering database from the utility, and we import it geospatially via Swift and link it to its stands. And this then facilitates easy comparison of predicted kVA versus metered kVA. So what we are aiming to achieve with Edison is creating an integrated database whereby we consolidate various data sets into one geospatial network model. Future data sets that we want to incorporate is climate data, solar irradiance data, and then also an important one, building footprint shape files, which will aid in studying commercial and industrial demand density metrics, and then any other relevant metrics that will aid in studying load behavior. Now, in terms of the calibration process, we know that we obviously introduce error, and there This is due to two different factors. So first of all is the fact that the consumption, the energy consumption resolution is per month and not ideally as you would like daily 30 or even 5-minute resolution data. So we know with an increased averaging interval comes a loss of visibility in the variability of the consumption. And now the question arises, to what extent? How can we quantify the area that we introduce? And also, how can we compensate for the area that is introduced through a calibration process? And this is an important question that needs to be answered, and things that we at the SAIEE Load Research Chapter will need to look at. Then also the second part of the area is making the jump from energy to demand. So this inherently introduces error even with high resolution accurate consumption data. And once again the question arises, to what extent? What error is introduced? How can you quantify the error? And then how can you compensate for the error? And that is also a very important research question. It's a matter of taking the information that we have, which is the energy consumption, and using that to predict demand values. We know that we're introducing error, but the study question now is, how can we quantify the error that we introduce, and how can we compensate for it by means of calibration? So what we do is we typically acquire 5 or 30-minute data at HVMV substation level, if available from the utility. Currently, we also have an ongoing project whereby we have strategic mini-sub metering for a specific client. Because we are studying load behavior, we want increased downstream visibility, and this will later on be extended up to LV kiosk level, and ultimately also installing meters at end user level to aid us in studying load behavior. So we use metadata to calibrate downstream loads, and in Edison we employ an automatic load scaling functionality. So this can be applied on a per stand level. You can do it per load class. You can do it per supply zone, which can be your kiosk, transformer, distribution or substation zone, or you can do the automatic scaling on a per user selection. So in future we are looking at employing automated curve fitting algorithms whereby auto calibration can take place within a specified set of rules and limits. So the calibration also has two components to it. There's amplitude calibration and there is shape shifting. So shape shifting, and this is where I want to get back to the SCMGLF load factors and power factors that we are using. So I mentioned I use the phrase on first iteration. We use the SCMGLF load factors and power factors. So what this means is, on our first iteration in studying this load behavior through our software package, is we don't know what the current load profile shapes look like. So on first iteration, it is a very useful approach to use what we already have in the SCMGLF standard, using those shapes and the load accompanying load factors and power factors, and then going through the process. But now, and a very important question that needs to be answered by the SAIEE Load Research Chapter in terms of shape shifting is, what do the new shapes look like? Because the onset of a change in customer behavior due to electricity prices and all kinds of lower consumption and smart electricity devices, the onset of distributed generation, and ultimately battery storage will significantly change the traditional profile shapes that we have come to know over the years. From normal passive loads, we've got your normal, for residential consumers, you've got your morning peak, your dip during the day, and your evening peak. The important question now, and what we will need to learn over time, is what do the new shapes look like? And ultimately, answering the question, will we learn that we can come up with different customer groupings? And what I mean by that is the traditional notion of grouping customer behavior according to LSMs. Is that still valid? Or can you now see situations where within one particular LSM customers can behave vastly different? And eventually, a question that needs to be answered is, should we look at different ways of grouping customers, clustering them on similar behaviors rather than taking metrics such as LSM to group them. So it's an exciting time and a lot of important questions need to be answered. But ultimately, as we go through this process of acquiring large data sets, consumption data sets, and using that in predicting demand, you acquire databases and you learn through each application something new, which eventually can lead to a very useful output in studying modern load behavior. So we also capture the calibration information, and that is to study the relationship between consumption and demand. We need to keep record of the calibration metrics that we had to apply. We need to know how we needed to compensate for the errors that we introduced and keep record of that. So in terms of load forecasting, the future load growth pockets, we also incorporate geospatially into the Edison network model by means of a shapefile. And in that shapefile, we document the location of the new development, the size, the anticipated land use, when the development will start, and also how long it will take until the development is saturated. So this we base on STFs, IDPs, house plans, etc., and we workshop that with town planners and electrical departments. Different growth curves can be employed in Edison. You can use linear curves, step curves, S-curves, or customs. And this facilitates scenario-based planning between two extremes, which is your current situation and then ultimately saturation. You can also model, in terms of your current loads, a change in behavior, which can be a stagnation or growth or decline, as we have seen for a particular client that I made an example of earlier in the presentation. And then once again, you can employ linear, step, S, or custom growth curves. You can also then model the impact of distributed generation and different demand-side management strategies. So this is just to show you how it's done, where the existing network is taken and there's a future network overlaid on top of that, and then you can do your demand forecast. This is the particular client that I referenced earlier, where I showed you the network. So this is also just, these are the future development areas, also color-coded according to the different supply zones. So we incorporate the future development areas geospatially into the network area. So before I get to the closing remarks, just a quick summary of what you've learned today. What we do, so we compile a geospatial database with energy consumption data for all these stands in a particular network. And this database is informed by extracting data from the municipal or utility billing database as well as from prepaid vendors. And then we use the as measured energy consumption patterns. We incorporate them in geospatial format in the network, and we incorporate them into the network, and then the energy consumption is then used in a predictive process based on the known energy consumption patterns of a stand in order to determine the demand patterns thereof. So in terms of the closing remarks, load behavior needs to be actively studied to keep trend with the status quo, and that is why we have something such as the SAIEE Load Research Chapter. I've shown today that the GLS methodology is a work in progress, but we have powerful tools to support the load modeling process, and we invite input from all relevant stakeholders. So we know that available data is limited, but it's a question of how do we best use the data that we do have access to, and then also how do we go about sourcing the necessary data that we need. And the more times we do this, the more data we will acquire and the more informed we will be. And that refers back to the flow chart that I was showing earlier. It's a refinement process where we rinse, repeat the methodology, and we learn through it, and then we adjust and ultimately come up with valuable information that will aid in studying load behavior. Thank you very much.